Okay, today is tree diagrams. So first of all, let's just talk about a simple probability question. You flip a coin, but then you make it a little more complicated by saying you flip it twice. Now all of a sudden the sample space, notice me using a big scary sounding word, is bigger. Because what are the things that could happen? Heads, tails, and what else could happen? Tails, heads, and heads, heads, and tails, tails. Good. Those are all the things that are possible outcomes. That, again, is called the sample space. All right. But that alone does not tell you exactly like how to get the answers. Whereas a tree diagram, if you do it right, really does. So here's a tree diagram. And what do you think this split is? It's like a choice in the road. It's going to either be heads or tails. Good. And it doesn't matter what you put first, but I'll just starting with the heads. Then this people often get confused as two separate events, that or that, but really this whole thing is the second coin flip. And I just don't know which one to use yet. Because that depends on whether I get a heads or a tails. All right, so the rest of my tree is in this middle column here, is all about what happens on the second flip. Thank you. So now, this would be really, really simple if I just kept it all as 50-50s, but then it won't teach you as much. So I'm going to make this a weighted coin. I know it's very difficult to do this, but imagine for a moment that somebody has designed a coin that when you flip it is more likely to turn up heads than tails. Okay? Let's imagine that it's a 60-40 split. Everybody put 0.6 and 0.4 there, because total, do you get that has to add up to 100% or 1.0? All right. Now, on the next one, it's still a 0.6 and 0.4 because nothing's changed. When you flip the coin, you still got a weighted coin, right? So it's the same exact numbers. And so there's also a 0.6 and a 0.4 here. Now, here's the really important part. You need to summarize your chart. This is the beginning of a tree diagram, but it's not the end. The final tree diagram is where you sum it all up. Why am I putting a 36 here? I multiplied the 0.6 and the 0.6, and I got 0.36. Why? Because that's the probability of me getting heads, heads. I'm going to move it over a little bit and throw in a heads, heads, because that's a summary of what happened on that branch. Next, let's summarize this next branch. It was heads, tails, and the probability is going to be, I'll do that in black again, 0.6 times 0.4, 0.24. Any wild guesses what's going to happen on the next one? It's the same. How come you know it's the same? Same combination of two numbers being multiplied, and if you multiply it and reverse the order, it's called the commutative property. It stays the same answer. So 0.6 times 0.4 is 0.24 again. And the last one is different than all the other ones. And it's what? Tails, tails. And it is what decimal? 0.16. Now, I'd like you to ponder these numbers. What do they add up to? 1 or 100%. Okay. Now, if I asked you what's the probability of getting heads, heads, technically 0.36 is right, but you always are supposed to divide by something. By 100%, but what? By 1. Why would you need to do that? You don't have to do that, but when the problems get more complicated, you're going to need a denominator. And do you get, if anything is possible, then you're dividing it by all of these things added together, and they all add up to 1. They're all possible, so all the possibles go on the bottom added together. I'm going to reemphasize that by just showing this. 0.36 plus 0.24 times 2, because there's 2 of those, plus 0.16. That's all of them added up. which adds up to 1. Again, why am I banging on this drum so loud? Because in a moment I'm going to say that not everything was possible, because I saw that when they flipped the coin, that their second coin flip was a tails. I don't know anything else, but I know that the second time they flipped the coin, they got a tails. Now it's the probability of tails, tails. It's what you want over what's possible. What's tails, tails? 0.16, but I changed the possibles by saying I know they got a tails on their second flip. So it can't be this. What else can it be? Tails, heads. It can't be that because I know it had a tails on the second flip. So do you get those two are the only things that are possible? This one and this one are the only things possible. So where do they go? On the denominator. So then it's 0.24 plus 0.16. And that is a 0.4. Okay. There's another way you could have done that, but this is the best way to get what's happening. It's what I want, which was tails, tails, over all the things that were possible. Add it up. Yes?
Is there any reason to move the tree horizontally and not vertically?
I get what you're saying. Trees kind of look more like this, Mr. Server, when they grow out of the ground. I hear you. And if you want to do it like this way, it's almost like the roots then. And I would be totally fine with you drawing your trees that way. I will say that all the keys are going to be going from left to right, but there's no mathematical reason that they have to. Okay, so back to where we were here. This little tree diagram, I'm going to undo a bunch of stuff here, get it back, that we've made can answer so many questions. That's what's really good about trees, is you can answer like a million questions from this. So I'm going to ask you a few more, and I want you to write what you think the answer is. Often you have to add a couple things and put them on the top, in which case just leave them that way, like 0.36 plus 0.24 over 1. And always make your fraction have a denominator, even if it's over 1. So you're going to read me an answer like that. And I know that simplifies to 0.36, but it also reminds you that there is a denominator. Okay, so when you have your answer, turn it my way. Here's my question. What's the probability of, hold on just a second, pausing. Okay, so what is the probability, given that I know he did not ever get a heads, that he got tails, heads? He never got a heads. What's the probability that he got tails, heads? Yeah, it's a trick question. Because if you never got a heads, how can you get a tails, heads? That one's just a thinking question. Okay, but if you were going to do it this way, you might say tails, heads is 0.24 over what were all the things that were possible. 0.24 isn't in the possible. That's what breaks the rules here. If I narrow this down to just only things that were possible, if I never got heads, it can't be any of these. So that's the only thing possible is 0.16. And then what I want is not on the list. There's nothing I can put here. Nothing I can put there. 0 out of 0.16. Okay, that's why it's 0. So now back to this. Here's another one that's a little trickier. Given that he got a heads, but I don't know if it was first or second, but you know he got a heads, what's the probability that he got heads, tails? All I know is he told me afterwards that one of them was heads. He didn't tell me if they were both heads or not. He just told me one of them was heads. What's the probability that it is tail? Did I say tails, heads? Heads, tails. Okay. You're right. Yeah, it's going to be 0.24 either way. But tails, heads. Given that one was heads And I should even say at least one was heads. Okay, so tails heads is this one, 0.24. That is not the right answer, though, because I got to divide it by something. All the things that were possible. I know he got a heads. That means the only thing that's not possible is tails, tails. So I'm adding up the other three. Does that make sense to you? How many of you knew that? Okay, good. So one more that's like that. Given that he got a heads first, what's the probability that it was heads, heads? Given he got a heads first, what's the probability that it's heads, heads? You might be tempted to just say it's 0.36 because that's what heads, heads is. But that's not it. Because given he got a heads first, means there's only certain things are possible and you put them on the bottom. I'm not sure if you answered it, Dylan, because I haven't actually divided them, but he's probably right. Okay, good. Yes, that's what I was looking for. That's what I was looking for. Yup. You have two things in the top, and that can't work. That's what I was looking for. That's what I was looking for. Yep. If they add up to, yep, that's right. Yup. 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 Do you have an answer? Yup. 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 Pretty much everybody's getting this one. The two things that were possible were these two, because they had a heads first. 0.36 plus 0.24, and you could actually add them together and get 0.60. So 0.36 divided by 0.60. All right, it's always what you want over what's possible. See how this keeps coming back? Want over possible. Okay, next let's talk about why we're multiplying these things. Whenever you have probabilities, multiply them. If you have a complete probability, you multiply it by another one. That's a probability of a heads. That's a probability of a heads. You multiply them. But do you get why these got added? Because those were the things that were possible, and you want to add up all the things that are on the bottom that are possible. All right. I'm going to give you one more question off of this. What if you win? If you get heads, tails, or tails, heads? Given that you got a heads somewhere. You win if you get tails, heads, or heads, tails. As long as you know that, I guarantee you, the person got a heads somewhere. You do not have a 100% chance of winning. If you think you did something wrong. You didn't add them on the top. There's something added on the top, otherwise you're doing it wrong. Yep, 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 yep. Top's wrong, unfortunately. Yep, yep, yep. Okay. Yep. So how do we get the 48 on the top? Yep. Heads, tails, plus tails, heads, which is 24 plus 24. I thought you just said, Mr. Server, we're supposed to multiply probabilities. If you have probabilities that are complete, then they can be multiplied together to get the next probability of two things happening like in a row. Okay, this is just the probability of one thing happening. So this or this can happen, or is a sign for add. You don't always multiply probabilities every single time, but most of the time when you're doing these problems, you're going to end up multiplying two separate probabilities to get the third one over here. That's the combination of the two. Okay, anyway, this one's adding on the top, and then on the bottom it was like 0.80 something. And that, what's that from? All of these are possible. You're right. They're all possible, so you add them all up, and it's 0.80. What was it? 4. Thank you. All right. Cool. I think you get what you need to be able to do this stuff. Now, let's. There's a couple other little slides I want to talk about. So everybody, fast forward down here through. This is a good one. You can use logic about these charts to figure out A. Once you figure out A, you instantly will be able to figure out B. Who's already got A? Couple people. Because why? What did you do, Mr. R? What do you think the answer is? How about that? You were doing it different? Okay. Who's got what they think the answer is? What do you think the answer is?
0.8.
Okay. Okay. So if you say it's 0.8, why? 0.7. Why?
Because with the quarters ones, we multiply the tops.
Uh-huh.
It's like 6 times A equals 42.
So 6
times A equals 42. 0.42. So it's like an equation.
So it's like an equation. Yeah. Yeah. This times this has to equal that, or you could divide it. So you could take 42 divided by the 6 and get 7. But either way, 6 times 7 is 42. Do you guys get that it's 0.7? Okay. If this is 0.7, instantly, you change this A to 0.7, and you know another one. 0.7. What's the other one? 0.3 for what? B. B has to be 0.3 because these have to add up to 1. Good. Now you can do the rest of them. You can figure out all the rest of them. I'll pause for a second while you try to figure out the rest. This one's 0.7, this one's 0.3. I'll pause while you try those. Okay, so let's see if you did it right. The next one I can figure out is D as in dolphin, because 0.6 times 0.4 makes 273. Nope, just making stuff up. I had a lot of people look at me like, what? It's just because these two add up to 100%, so that's got to be 0.4. Okay, if that's 0.4 and that's something and it makes 32, 8 times what makes 32? Nope. I just said it backwards. 8 times 4 makes 32. There we go. That's got to be 8. And then if that's 8, this has got to be what? 0.2, because they have to add up to 100%. And then I could do this G 2 different ways. The way you were just saying, which is that these all have to add up. And what was C, by the way? That was 0.18. And I could do this based on all of those adding up to 100%. Or it's, I think, easier. Just go 0.4 times 0.2 and make point what? Careful. 0.8. If it was 0.80, it wouldn't add up. This right there wouldn't be enough to make it more than 1. It has to be 0.08. Okay. Now that we've got that done, that is a typical, like, that's how you can tell what the other numbers have to be. These things multiply and equal these, and these things together have to add up to 100%. That plus that has to add up to 100%, etc. Okay, I think that we've done enough that I think you're ready to start your homework together. I want to warn you one last thing. This is a nice slide for showing you if you're going to have 3 things happen, your first choice sometimes is as simple as one choice. But then your second choice, look at it, it's getting more complicated. It goes in here. That's just one second choice because you don't know if it's going to be this or that way that you go down the road when you have this choice of this way or this way. But then it gets the worst way off to the right. So when you're drawing your charts, make sure you leave plenty of room off on the right because the right side is where it gets really messy. Yes, sir. Okay, I'm going back to this one. 0.42 and 0.18 are supposed to add up to 0.6, and I think they do, don't they? Yeah. I think they do. But yes, that is a true statement that these two together are going to make this one. And these two together are going to make that one. It's a nice pattern. Okay, back to independent versus dependent. This is important to understand. Okay, if I have a deck of cards, and I happen to have one right here. These are kind of cool ones. Did I show you this deck yet? All right. These are kind of cool ones because going up in value lately. They're gold plated. 0.999 as in pure gold plated. Now I know you'd think that would make them incredibly valuable, but gold plate is so thin and it's relatively cheap to do that these are regular playing cards that have been coated in gold and yet aren't that expensive. It's like 20 bucks. So I get what you're saying. You know, like could you like melt this down so that you get just the pure gold from it? But it would be so little. Yes, they can scratch. So. Wow. So you're saying basically the reason it can happen is because this can be so thin, such thin amount of gold that it really wouldn't add up to almost anything when you actually flake it all off and get it in a little pile and stuff. You know, there's some drinks that have gold in it. Have you ever seen that? Yeah, I think there is ice cream that's got shavings that are got your gold in it. Yes, they actually have these little gold shavings in food sometimes. And it's actual gold. I know it seems crazy, but if it's thin enough, even if it's really valuable stuff, if it's super, super, super thin, they can keep it cheap enough. Okay, so anyway, these are gold playing cards. Now, if I have you pick a card out, pick a card, any card. Oh, that was close. Because this one would have fit you even better. You were only one away from it. Anyway, so he's got a card. You can look at it. Okay, this is not a card trick. I have one of those for you tomorrow, but this is just me demonstrating probability. What was the chances that he would get the ace of spades? 1 out of 52. Good. What's the chances that he would get a spade? 13 out of 52, or some other kids are saying something else. 1/4. But 13 out of 52 is 1/4 because there's 13 spades in the deck. If you don't know what all the things are that are in the deck, that's something that you got to get good at. We can put up a slide for you to help you because we do get some of you guys would be at a disadvantage on tests if we don't tell you all the things that are in a deck because you're supposed to know. That's called cultural bias. Okay, so if you have a playing card question on the ACT, you'll never see that because that would give some people who play cards an advantage over people who don't. And so they try to be careful with that to not give things that are like biased. Okay, so anyway, what's the probability that he's going to pick the ace of spades now because he didn't already get it? 1 out of what? 51. Notice his probabilities improved, right? You didn't already get the ace of spades, did you? Okay, so now take another one, see if you can find the ace of spades this time. Where do you think it is? Totally not it. Okay, so now what's his probability of getting it the next time? 1 out of 50. You get how it's changing each time. Was this a dependent or independent example? Dependent, because it depends what he got. Because if he got the ace of spades, now I say, now what's the chance he gets the ace of spades? He'd have a 0 in, it doesn't matter, chance, because he's already gotten it. Okay? So does it depend? Yeah. If it's dependent, if the one depends on the other. Now, what if we do it different? Here, give me those cards back. Thank you. So now, what if we do this differently and I say, okay, pick a card, any card. Come on now, ace of spades, ace of spades. Oh, you were closer. Okay, still no ace of spades. Now, what if I have you put that back? Thank you. Okay, now find the ace of spades. Still not it. Okay, but do you get his probability was the same? Because why? put the card back, and that means that it wasn't dependent on what he got the first time. Okay, so that's independent versus dependent. All right, you guys got to remind me about the card trick tomorrow. It's a pretty good one. All right, so if I'm given a jar with 11 marbles, 5 red and 6 white, that adds up to 11. So I'll make my red ones 1, 2, 3, 4, 5, and then 6 white ones. I'm actually going to ironically make them black with empty inside, so that these are my white marbles. 1, 2, 3, 4, 5, 6. There we go. Then what's the probability of white then red? That's what this means. White then red, given no replacement. All right, there's a chart for that. On the first thing, he's either going to get white or he's going to get red. Do you get what I'm saying? What's the probabilities then that should go on these little branches? What's the probability of the white? Which is 6 out of 11. What's the probability of a red? 5 out of 11. Do you get that those total up to 11 out of 11? Okay, then for the rest of the tree, again, don't try to think of all the things that could happen. It's just white or red. Notice this needs 2 of them because we don't know which way it's going to go in the real world. Now, once again, do my numbers change? It says given no replacement. They do change. Because if he went down this road, what did he get? A white, and now he's not giving it back. So now my probability changes because he got a white, and now there's how many whites left? 5 out of 11. Thank you, 10, because there's 1 less marble in the bag, okay, or the jar. And so then this red one, there's still 5 red ones out of, how many marbles were there again? Do you get how I made that depend on what he got the first time? All right, it's really easy to just go along and say, oh, there's 11 marbles, so it's out of 11. It's out of 11. No, it's not, because you already got a red one. It's out of 10, out of 10. And if you already got a red one, then there isn't 5 red ones left anymore. There is 4 red ones left. And then there's still, though, all the white ones, which would be 6. Do these always add up to 100%? Look at that. They do. Does that make sense? All right, so that's how you do it if it's dependent. Sir?
So if we got one like that, then we have to go all the way until we get to 0.
Nope, because this says probability of white then red. That only implies we have to do it 2 draws. The first draw was this. The second draw was this area. The second, it always gets bigger as you go to the right. So the first pick was this part right here. And we don't have to keep going forever because there's only 2 draws. If they asked, what's probability of white, red, white, red, white, red, and keep doing that all the way out to, then you'd have to keep going with the chart. But realistically, it would get impossible to draw. Because you get how already to here, it's gotten big. The biggest we pretty much ever do is 3 trials. Because by the time you get to the 3rd one, it's like, whoa, huge. You don't want to draw those charts anymore. All right, so this is a deck of cards. Every card in the deck is right here. You have the option of asking me, if we're taking a test, to put that up on the screen so that we aren't being culturally biased towards people who play cards. How many of you have played cards before? That's most of you. But there's a few people in here not raising their hands, so I had to put your hands down quickly so they don't feel like, oh my gosh, I'm really weird compared to everybody. But there are people who don't know these things, and you have the right to ask me, because if you don't know the background, how can you possibly answer the question? But now that you see this, what's the probability you get a jack if you draw out of my golden deck here? 4 out of 52. It's out of 52. Unless I say, given I'm only using the red cards, then what's the probability you get a jack? 1 out of, how many of each kind? Only the red cards. There's 26 cards then that are red, and there's 2 jacks, so 2 out of 26, but it still reduces to 1 out of 13. So, all right. Now, if I only take the red cards, what's the probability that I get the jack of clubs? 0, because the jack of clubs isn't a red card. Okay, if jack of clubs is a black card, it was a trick question. That's this one on the top here. Okay, what about the probability that I get an 8? I'm using all the cards now. What's the probability that I get an 8 or a 9? Notice how I added. Or means add. 4 of those plus the other 4. I add them. Okay. What if I say, what's the probability of me getting an 8 and a 9? All right. Well, what's the first thing? Probability of getting an 8. What was that probability? 4 out of 52. 52 cards in the deck. Okay. And a 9. Do you get that implies I've already got the 8, and now I'm going to go back in and try to get a 9. So what is that? How many 9s are in there? We only took out 1 card. Remember? I know it was 4 out of, but we only got 1 card the first time. So now we got 4 out of 51. That's how you do the little more complicated ones. Notice the denominator has to go down by 1. That would be an 8 and a 9, and you'd multiply your probabilities together. This was the probability of an 8. This is the probability of a 9 after you already drew an 8, and you'd multiply them. All right. I think that's enough of the new stuff for today, so let's get to the homework and take a look at it with me. It looks like neither one of those. Hold on just a second. Okay, so here's your first problem, and I want to warn you, you want to zoom in a lot to draw this one so that you can keep it crisp even though it gets big. All right? You choose 2 cards one at a time. Boom, right there. This is the whole first column goes like this. The writing will eventually appear. Or not. Okay, I'm going to try again. It's not going to let me write on it. That's okay. The whole first column is your first choice. I'm going to pause for a second. All right, so here we have our picture, except this time, hopefully, I can write on it. Yes, I can. And the first event happens here, and that is either you're going to get a club, a spade, or, oh, I need more rows, a heart, or a diamond. I would recommend C, S, H, and D. Otherwise, you have to write them all the way out. But I'll know what they mean. There's only one C logically. That must be the clubs. Okay, that's your first draw. Why is the second draw more complicated? Yes, there is one less card. That's very important. It says you do not replace the first card. Very good. But that wouldn't be that much more complicated. But I don't know whether I'm going to get a club, a spade, a heart, or a diamond. So you have to have a contingency possibility for each. If I get a club, then I could do it again. See what I mean? Clubs, spades, hearts, diamonds. But that's it. We're not going to make you go further than that. But you have to do that for each thing. So that means a total of 16 branches on this tree. So here's what you write on each one. I don't recommend that you write 1/4, 1/4, 1/4, 1/4, even though that's true at the beginning. Because you want to think of it as out of 52 cards, and there's 13 out of 52 here, 13 out of 52, 13 out of 52, 13 out of 52. Why should I do it that way? Because then you'll think about it as you write the next one. What happened when I went down this road? What does that mean? I got what? A card. What kind of card? I got a club. So therefore, there isn't 13 out of 52 for this next one because I already got a club. So what is it? Nope, there isn't 13 left because I got one. 12 out of 51. You get why there's one less? Because I got one. So are all of them 12 out of 51? No. Then the spades, there's still 13 left. Why? Because I got a club. And it's still out of 51 though. Good. Now, do you remember me saying that the most important part of the chart was this end part? It is. That's where you take your calculator and you multiply them. Would you please multiply for me 13 out of 50, actually, let's make it simpler, 0.25, because this one is 0.25, times 12/51. 0588. That means there's about a 6% chance that that would happen. Club and then club. I'd like to try it. Let's see how lucky you are this time. A club and then a club.
I think they're gonna be right by each other. Actually,
That is a,
right by each other. Actually, yeah.
that was a good idea. It's just you got both hearts.
Oh.
It's a good plan though, because you knew I had kind of sorted by deck, so that was a good theory. You had actually more like a 1 in 4 chance because you could have got 2 clubs, 2 hearts, 2 diamonds. There's always a chance you could have again had 2 that are right next to each other, like here's the clubs and here's the hearts, and you could have got 1 each. But it was a good theory. Didn't work, but it was only a 6% chance it was gonna. So what was there a percent chance you weren't gonna?
I want to see all the clubs.
94%.
Where is everything?
Yeah, like I'm telling you, get the ace of spades. There is no ace of spades here. Go ahead and look. You can look through it.
Alright, cool.
I think you'll find it there. Okay, so this is the beginning of the chart, but I did not finish it. That's your job. But I'm only going to ask you to do 2 charts, that one and the next one. Okay, so you may skip the very last one. This one is assigned plus the questions that are about it. And I'm going to pause, or I'm going to delete the ink on this thing if I can. Clear. Where's clear? Clear ink. Okay. Then I'm going to slide down. And I want you to do the sock question also. And you need the diagram. And then the last thing is you can skip. I'm going to let you skip this one about the marbles in the bag. We did one like that before already. So, okay. So these are intense to make, but do a good job of them. I'm only assigning you 2, and that makes it that's a reasonable compromise. I make it easier for you, and you actually do it. Okay? That's all I got for you for today.